Probability, mutually exclusive and non-mutually exclusive events. So these probabilities involve scenarios where we'll be using the word or, right? Which means we're going to be adding probabilities, this or this. So let's say we start with a standard deck of 52 cards. What is the probability of drawing a heart or a spade? So let's say we do a Venn diagram for this, right? Since there are no hearts which are also spades, we do not need an overlap, right? So there is nothing in the overlap region. There's no card which is both a heart and a spade. There are 13 hearts, there are 13 spades, there are 26 other cards which would be clubs or diamonds. So the probability of heart or spade, right? So remember, this is union, which is associated with the word or, which is associated with the operation plus. So the probability of a heart or spade, and keep in mind, when we're talking about this mutually exclusive and non-mutually exclusive, we're talking about doing only one thing. That is, we are drawing one card. So, probability of a heart or a spade is the probability of a heart, which is 13 out of 52, plus the probability of a spade, which is 13 out of 52, which total 26 out of 52, 1/2, right? 0.550%. Now, the other way to think about probability of a heart or spade is the number of cards which are hearts or spades, right? Which is 13 plus 13, over the number of cards in the deck, which is 52. So that's another way to think about it. One is as a sum of probabilities, right? There are 13 hearts out of 52 cards, favorable over total. There are 13 spades out of 52 cards. Here, there are 26 cards. This is the number of hearts or spades out of the total of 52. And these are mutually exclusive events. In other words, they both can't happen. Both can't happen. Mutually exclusive. You cannot draw a card that satisfies both. There are no cards which are both a heart, both a hearts, and at the same time a spade. So both a heart and a spade. No common elements. Sets are disjoint, right? We're not going to draw this. The sets are disjoint. They have no common outcomes. Now, given a standard deck of 52 cards, calculate the probability of drawing a heart or a 10. So here's the universal set, which consists of hearts and tens. There are 4 tens, right? But I'm not just putting 4 there because one of those tens is also a heart. So there's one card which is both a heart and a 10. There are 3 other tens, right? Because there are a total of 4 of them. So the 10 of diamonds, the 10 of clubs, the 10 of spades. There are 12 other hearts. The ace, 2, 3, 4, 5, 6, 7, 8, 9, jack, queen, king. We have a total of 12, 13, 16 cards. So there are 36 other cards remaining for the total of 52. Now, let's say we just did this without doing that. If we just counted, the probability of a heart is 13 out of 52. These 13. Man, I can't go backwards. The probability of a 10 is 4 out of 52, these 4. But if we do that, we count these, right? We're going to say 13 and 4 is 17 cards, which could be a heart or a 10. But in reality, there are 12, 13, there are 16 cards. So from that, we have to subtract this one card, which has been counted twice, which is the probability of a heart and a 10, right? The intersection. So minus 1 out of 52, right? There is one of the 52 cards, which is the 10 of hearts. So using just the formula and not bothering with the Venn diagram, we have to worry about the and probability, right? right? So this is, and leave this, don't go, this is 1/4 and this is 1/13, right? If you reduce these probabilities to 1/4 or 1/13, you're not going to be able to add them. So in order to do anything where you're going to be adding probabilities, just leave the denominator. So 13 plus 4 is 17 minus 1 is 16 out of 52, which is 8 out of 26, which is 4 out of 13. Okay, and generally when we're dealing with probabilities with cards, we pretty much like to leave it as a fraction if we can. So the probability of a heart or a 10, union 10, put them together, is the probability of a heart plus the probability of a 10 minus the probability of the intersection cards, which are both hearts and 10s. And another way we could do this is by doing numbers. The number of hearts, so there are 13 hearts, plus the number of 10s, which are 4, minus the number of 10 of hearts, right, over the number in the deck. So 13 plus 4 minus 1 is 16. So drawing a heart and drawing a 10 are non-mutually exclusive. So remember, mutually exclusive is both cannot happen. Non-mutually exclusive says both can happen, right? In this case, there is a heart, which is also a 10, right? The 10 of hearts. There is a common element or elements. The sets are not disjoint, right? And basically, the intersection has something in there. All right, let's use the chart at the right to help with the following. So in this chart, what we're doing is we're throwing 2 dice, right? So you've got the first die, you've got the second die. So the first die can be a 1, a 2, a 3, a 4, a 5, or a 6. The second one could be a 1, a 2, a 3, a 4, a 5, or a 6. And the table is the sum of the 2 dice. So generally we're playing a dice game. We roll the 2 dice, we roll the dice, we can get a total anywhere from 2 to 12, right? 2 would be a 1 on each die, 12 would be a 6 on each die, 3 you can get by rolling a 1 and a 2, 1 on the first die, 2 on the second, but you can also have 2 on the first die, 1 on the second, so there are 2 outcomes. So determine the probability of rolling a sum of 11 or a sum of 4. Okay, so remember this. So separate these off. Those aren't our sums. So a sum of 11 or a sum of 4. So the probability of 11 or 4 is equal to the probability of 11 plus the probability of 4. Now, question is, are these mutually exclusive? Are there any sums which are both 11 and 4? And the answer is no. The probability of 11 is 2 out of what? No, we better count, right? What are the total outcomes? So we can see the outcomes are listed here in this table. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 6 is 36. So probability to get 11 is 2 out of 36. Now don't reduce anything because we're adding. Probability of a 4 is 3 out of 36. And that would be 5 out of 36. So the probability of getting a sum of 11 or a sum of 4. Now, what if we tried to do this and said the probability of 11 and 4? Well, there are no outcomes which are 11 and 4. So if you chose the formula for non-mutually exclusive, that is, both events can happen, you would find out that the probability of getting an 11 and a 4 is 0. So they are mutually exclusive. You can get an 11 or you can get a 4, but you can't get both. So we don't need to do that. All right, let's move on to the next one. So the probability of rolling a sum of 8 or 2 of the same number doubles. So here's a sum of 8. Right, so 6 and a 2, well, 2 and a 6, 3 and a 5, 4 and a 4, a 5 and a 3, a 6 and a 2. And doubles, 2 1s, 2 2s. Now we can see these sets are not disjoint, there is overlap, and that is when you roll a sum of 8 and you have doubles, you have double 4s. So the probability of rolling a sum of 8 or doubles will be the probability of an 8 plus the probability of doubles minus the probability of 8 and doubles. Okay. Now, one way to do this, of course, would just be to count 1, 2, 3, 4, 5, 6, 7. Don't count this. 8, 9, 10, and say there are 10 ways. But it's a lot easier just to say there are 1, 2, 3, 4, 5 out of 36. 5 of the 36 outcomes are 8. 1, 2, 3, 4, 5, 6 of the outcomes are doubles. 1 of the outcomes are doubles and 8. 5 plus 6 is 11, minus 1 is 10 out of 36, which reduces to 5 out of 18. Okay, so using the chart, without having to, if we use the chart, we don't have to actually make these marks, right? We can just do a straight count out of the chart. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, and 1. Determine the probability of rolling a sum that is an even number. Sum that is an even number or an odd number. So let's take squares around the even numbers. 6 even, 8 even. Okay, rectangles, maybe not squares. And then let's circle the odd numbers. Okay, so probability of rolling a sum that is even or odd. Are there any numbers which are both even and odd? So the probability that it is even or odd is the probability of even plus the probability of odd. Now, are there any numbers which are both even and odd? The answer is no, so we don't need to do this. Probability of even and odd. Even numbers, well, let's base it at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 out of 36. Odd numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 out of 36, which is 36 out of 36, which is 1. So there is a 100% probability of getting a number which is either even or odd. I mean, think about it, that's all you can get. Numbers are either even or odd. There's no other type of numbers. All right, let's say we're playing cards. Calculate the probability of drawing an ace or a king. Ace or king. Well, there are no kings which are also aces. So it's the probability of drawing an ace plus the probability of drawing a king. Now remember, we're only doing one draw. So 4 of the 52 cards are aces, 4 of the 52 cards are kings. There is no overlap, so we don't need to put in anything here, which will be 8 out of 52, which is 2 out of 13, right? And if you're having any problems reducing, just go 8 divided by 52, math, enter, convert to a fraction, enter 2 out of 13. Calculate the probability of drawing a diamond or a face card. Probability, diamond or face. The probability of a diamond plus the probability of a face minus, so are there any cards which are diamond and face cards? And yes, there are. The jack of diamonds, the queen of diamonds, and the king of diamonds. So 3 out of the 52 cards are diamond face cards. Diamonds are 13 out of 52. Face cards, there's 3 in each suit, right? So that's 12. Sorry, yeah, and there's 4 suits. So 12 out of 52. So probably what we don't really need to do here is a Venn diagram, right? We can just do, based on our knowledge of cards, 13 of the 52 cards are diamonds. There are 3 face cards in each suit. So the Jack, Queen, and King of hearts, the Jack, Queen, and King of diamonds, of spades, and of clubs. So that's a total of 12. But if we count twice, right, we will have counted the diamond face cards under the 13 and the diamonds and the diamond face cards as the face cards. So if we counted them twice, we have to subtract that off. Remember, we're not going to reduce these. We don't want to reduce because they all have a common denominator. 13 plus 12 is 25 minus 3 is 22 out of 52, which would be 11 out of 26. Okay, and again, any of these can be converted to decimals, and then you kick the decimal 2 places to the right, and you've got a percent. So decimals or percents. All right, probability of Ms. McKay. All right, so draw a Venn diagram. So in this case, we really want to draw a Venn diagram because we get this 0.6 and 0.5, which already adds up to more than 1. So we know that what is in the Venn diagram must add up to 1. So we've got gardening, we've got schoolwork, and what we do know is we've got 0.3 out here, which means that what's in here, here, and here must add up to 0.7. So 1.0, which is in the whole box, right? The whole box has to add up to 1. This, 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 and this. So these 3 guys here have to add to 0.7. Now the problem is, lunchtime, go eat lunch. The problem is that these add up to 1.1. So we have 1.1 to deal with, but we only want to have 0.7. So that is 0.4. So the overlap here is 0.4. 0.4. 0.4 is in the overlap. Now gardening is 0.6. So gardening only 0.2. Gardening and schoolwork 0.6. Nope, sorry. Yeah, only gardening and schoolwork is 0.4. So just gardening is 0.6. Gardening and schoolwork is 0.4. Only gardening is 0.2. Inside the schoolwork, we need 0.5, and we already have 0.4. So only schoolwork is 0.1. Gardening and schoolwork is 0.4. So all of these, so 0.2 plus 0.4 is 0.6, 0.7, 1.0. Okay, so we're good now. Are the 2 events mutually exclusive? No, there is definitely some overlap. I mean, even just from this, you know there's overlap because that probability adds up to more than 1.1. So, state test. God, how many typos are in here? State the probability that Ms. McKay will do at least one of the activities. So 0.2 plus 0.4 plus 0.1. So it's gardening or schoolwork or both. So the probability, which really is just gardening or schoolwork, Gus, would be the probability of gardening plus the probability of schoolwork minus the probability of gardening and schoolwork. Now, that's if we wanted to use the formula, right? Which we don't need to. It just says state the probability that she'll do at least one. So we can just look here and go 0.2 plus 0.4 plus 0.1 is 0.7. And we can't do any of this without knowing this probability here, the and, which we couldn't have gotten without doing the diagram. But if we plug in gardening 0.2, gardening 0.6 equals 0.6 plus schoolwork 0.5 minus 0.4. 1.1 minus 0.4 is 0.7, right? Which we could state simply by adding these 3 up. Okay, so from a Venn diagram, you don't need to use the formulas, but you can use the formulas, but keep in mind, without the Venn diagram, you wouldn't have this number. State the probability we'll do some gardening, but not do any school. So gardening only, 0.2. So very useful in this case to actually fill in the Venn diagram, right? And it uses the same ideas that we used back in, wait for it, back in set theory, right? So set theory, counting principles, probability are all very closely related, right? This diagram is filled in using the ideas from set theory. Next up, expected value. If the probability of an event is P, I actually did one of these earlier, the grad and the females, I think. The probability of an event is P, then the expected number of occurrence of this event in N trials is N times P. So if you think about it, the probability of tossing a coin and getting heads is 0.5, 50%. If we do that 1,000 times, 1,000 times 0.5 is 500, right? So the expected value is the number of trials times the probability. All right, let's use that. In a game of chance, a player spins a round spinner labeled 1, 2, 3, or 4 and wins the amount of money shown. Assuming the probability of spinning a 1, 2, 3, or 4 are all equal, so in that case we would expect to see a spinner divided into quarters. Oh, here, let's throw in the quadrants. Does that matter? We don't do much with quadrants. Never mind. Whatever. So 1, 2, 3, and 4 are equal. Determine the expected return on a single spin. Okay, so the expected, oh my God, how many typos are in this thing? Or I gave it away for free. Okay, so spin number 1, so the probability of getting a 1 is 1/4. Now, that's not choose, right? That is 1/4 times $6. Or you get a 2, 1/4 times $3. Or you get a 3, 1/4 times $1. Or you get a 4, 1/4 times $0. All right. We're going to leave everything as quarters, right? 6/4 plus 3/4 plus 1/4 plus 0/4. So 6, 9, 10. 10 over 4, which is 5 over 2, which is basically what we would expect is $2.50. Okay, so you spin, you're going to expect to win on average over the long run, right? This happens over a long time, any of these particular probabilities and numbers. Over the long run, you play the game enough, you're going to win $2.50 per spin. But it costs $5 to play. Is this a good game? No. Right? For every $5 I spend, I expect to get $2.50 back. So if it's a game and a charity thing where you're just looking to make a donation, then sure, go ahead and play. But if you're actually playing this game for money in a casino or something, never play this game. And if you are planning to ever go to a casino, make sure you understand probability before you go. An insurance policy covers a $20,000 sapphire ring against theft or loss. If it is stolen, the insurance company will pay the policy owner in full. If it is lost, they will pay the owner $8,000. From past experience, the insurance company knows oh my God, good thing you didn't pay much for this. Probability of a theft is 0.0025, and the probability of a loss is 0.03. How much should the insurance company charge to cover the cost of the ring? Okay, so for every $20,000 insurance policy this company writes on a sapphire ring, okay, so the expected value is the number times the probability. So they would pay out $20,000, okay, against theft, stolen, so that's theft. So $20,000 for theft, 0.0025. Or they would pay $8,000 for loss, 0.03. So let's work this out. 20,000 times 0.0025. Now we can do these separately just to kind of see. So that would be 50 plus 8,000 times 0.03, which would be 240. So $290. So for every sapphire ring that they insured, the probability of them paying out, or the expected amount they would have to pay out, would be $290. And the way insurance works is to spread that risk over very many policies. So I don't know how many $20,000 sapphire rings are out there that they're insuring, but they would be insuring a lot of jewelry. And so what they would decide is that your premium that you would have to pay would be a premium of $290. Now that wouldn't give them any profit. Okay, so they would likely charge a higher premium, but if they wanted to cover costs, the premium they would charge is $290. So for every ring, they could expect over the long run, over very many rings with these probabilities, to pay out $290. And we're done.